last lesson I teach all the forces things, right? Any problem with all those things?
No.
Okay, great. Okay. Dynamic. Okay, we'll first do Newton law. Okay. Okay, so what is the Newton first law? Can you remember? Anyone?
Action can start, change, or
Wow, very clumsy. You have any definition?
Yeah.
Yeah, you try. I remember that one.
Continues in a state of rest or uniform motion in straight line unless acted on by resultant force. Well, that's FMA.
Is that really what the Newton said? So clumsy. actually, last time I also learned like that. Okay, so I realized that he doesn't make sense. Newton speaks so clumsy one man. Okay, the Newton first law says this. When there's no resultant force, okay, when resultant force is 0, the change in velocity is 0. That's it. Does it include everything that you mentioned here?
Got the uniform motion in straight line part.
Now, the idea is that this thing is interesting. What is this? Velocity. When velocity, no change, right? It tells you speed, no change. And direction, no change. Okay? So it's very sharp. One sentence, that's what I say. Okay?
Okay.
So, because velocity tells you speed and directions also don't change. So, when you have speed don't change, but direction keep changing, do I need a resultant force?
Speed don't change.
Speed don't change, but direction keep changing. I changed my direction, but I didn't change the speed. Do you need a resultant force?
Yeah.
Do you need acceleration?
into the center.
Yes, you need, right? Okay, circular motion, small example, right? So this is why, right, the velocity tells you everything. Both directions and speed. And you say velocity don't change means both direction and speed don't change. That means if you're at rest, you're still at rest. If you're in a motion, you're still in a motion. And your direction cannot change. Okay? So one sentence, that's everything. So because of this, right, then it makes sense. Okay, so we say resultant force equal to 0, therefore there's no change in speed, that's the first law. Therefore, what if the resultant force is not 0? Makes sense, right? It should be the what he said the next. That's the second law. So what if resultant force not equal to 0 then? That's what the Newton said. That's what I say.
Second law is 0.
Try? Yeah. Try? Yeah, because it makes sense, right? I say resultant force equal to 0, no change in velocity. Then the second law comes in, of course, I say, what if it is not equal to 0? You must tell me what happened. Right? To finish the whole story. Equal to 0, this. Not equal to 0, this. Okay, what is the second law?
Then there will be an acceleration proportional to the mass of
F equals ma.
No. Is that in the no, right? Put a change of momentum, right?
the rate of change of moment.
Yeah, okay. Now careful, okay, this is A level, different from O level. O level says F equal ma, but A level a little bit more refined. That's what exactly Newton said. Newton's law says, right, Newton says that if the resultant force is not equal to 0, the resultant force will be equal, the resultant will be proportional. That's the exact word it says. When you're quoting, you must use proportional, it cannot be equal. Okay, because you're quoting what he said. Okay, it says that the resultant force is proportional to the rate of change of momentum. Okay, so this one, right, tells you that but they say if everything is in SI unit, they will equal. That means if this is in Newton, this is in kg, this is in meter per second, this is second, then it will be equal because the Newton is made in this way. 1 Newton is actually made in this way, and the first guy created 1 Newton is actually made this way. So of course, when everything is SI unit, this guy got to be Newton, so it will be equal. Okay, so what do you have as an extension for this? You have this. Careful, okay? But I think one of them is not in syllabus too, so don't worry about it. Okay, therefore you have a product rule. So it depends, okay? Actually you have both components act together, okay? But the point is that in your syllabus, last time syllabus, also they will only test you this or this, okay? But now in syllabus, I think even this one don't test you. When in real life is the sum of them, okay? So what does that mean? Just time, okay? How do you detect this? Take a look at this. It means change in mass per unit time. Okay, do you have something that in motion which is change in mass per unit time? Okay, for any rigid body or the solid objects, these kind of things, right? It's not possible to have change in mass. Okay, okay. Now normal objects. Okay, so actually this is for fluid. Okay, when you have fluid, right? Your fluid, you flow. You have how many kg per second? Yet your speed of your stream of fluid can be constant. But there is a force there, so you use this formula for fluid. But this is for solid objects, okay? So normally, it's either one of them, we will not mix both of them.
So on that will be 0.
Yeah, so this be 0, then you go, okay? So if it is fluid, most of the time you look at it. Now, so how do you do questions at time? Okay, be careful about this. When things happen, right, you detect what's the number. If they give you 10 kg per second, okay, that means there is some mass increase or decrease per second. Okay, when you see this, think about the right hand side formula. Normally you will not have a change in speed, they will give you a constant speed. Okay, otherwise, right, you got to use that instantaneous speed with that instantaneous acceleration, that acceleration in mass, and that instant of mass to calculate that instant resultant force, okay, which is very complicated. Okay, so look at this kind of unit, can tell you which one they are testing you on. This is meter per second square, this is kg per second. Okay, normally this is fluid or fluid-like things. This is solid object. Okay, careful about this. This is the second law. The third law, when the force is added by object A on object B, okay, you will have an equal and opposite directions of a force B added back on object A. Okay. So these two forces are equal and opposite. Okay, they're equal in equal in values. Okay, and equal in nature. Okay, this one, and equal in value, equal in nature in all circumstances. Okay, in all circumstances. That means there's no such way you can make until the value are different. Okay. So, for example, you say this is weight, and this is n. Okay, this seems like acceleration pair, but it's not. Okay, because if you make the lift a downward acceleration at time, your weight is still the same. Okay, but the normal reactions from fall on the person is different. Okay, so this indicates that there is an instant that value is not the same. And nature, they are not the same because one is normal reaction, one is gravitational force. Okay, so nature and value must always be different to define this acceleration pair. Okay, third thing, right, you must know that these two forces must, if object A add things on object B, okay, these two forces are added on different objects, so they cannot cancel one another if you consider them separate. If you consider it together as a whole, these two forces both doesn't exist because it's internal. Okay, so when you need to find a force from object A to object B, object B, object, you cannot consider them as a whole to find any variable here because it would not appear in the equation. Okay, so do this, do that, or you consider this to find accelerations, acceleration you find something.
When they are moving,
Yes.
accelerating together.
Now, when objects are stick together and they travel in together, okay, the parameters are all the same. The T, V, A are the same. Okay, they must have the same T, same V, same A. That means all kinematic variables must be the same, and even the same as amount of distance you travel. Okay.
Is the force that they apply on each other
Force
the
is
same?
not the same. No. These two got to be the same. These two got to be the same. Okay, according to the third law. Okay, but the resultant force each one experience might be different because the mass is different, but acceleration is the same. Right?
Okay.
So all the kinematic variables will be the same. Okay? So use this idea, this and this can help a lot. Because you can combine them to find the A first. Let's say that the A is this guy's A, this guy's A, this guy's A also. Okay? So remember these are the variables, the kinematic variables are the same. Okay, so these are the 3 Newton law. And that's the whole thing about dynamic, right? What else? Oh yeah, we have a, do you have a impulse, impact, those things?
Just dynamics too.
Yeah, this the next one, right? Any problem with all this?
Can you do this question?
Sure.
Seven.
700 men stand on a scale or a floor elevator. The scale is called the force exerted whatever. It was the scale reading if the elevator has an acceleration of okay, yeah. Now the man, elevator, let's talk about a scale here and a man here. Okay. One leg easier. Okay. Now, so this man. Now, the idea is that let's consider this and the lift are together. Okay. So I have the man object and the continuous object with the scale. Okay. Of course, what I'm interested in is only the man, because why I'm only interested in mass, the man, because the elevator's weight is not given to me lah. The elevator external tension is not given to me lah. They only give me the things about the man. Okay, so let's just do the man. So the man, how many forces are there? How many forces are there?
His weight, the reaction.
Any more? His weight and the reactions, right? Any more? No more, right?
Yeah.
No more reactions, right? It's not moving left, right, so no friction whatsoever, right? Okay, so it's only up, down. Okay, so case one you say is 1.8 meter per second squared up, it's accelerating up. Okay, A. So what can I say? Okay, first you have acceleration, so drop to Newton's second law. When drop to Newton's second law, it says we don't say up, down balance, left, right balance, is no longer balance, right? So first, the man only have two forces. And it's accelerating upward. So resultant force equal to MA equal to R minus W. Make sense? This is what Newton's second law say, right? Okay? So the man is 700 newtons. So 700 divided by G time acceleration is 1.8. R minus W, because this is the, so N minus W, okay, this is N, this is W, right? It's accelerating upward, right? So you say that is the resultant force, so that force in that direction minus away the opposite one. they'll give you the resultant force. Okay? For example, we say 6 Newton, 2 Newton, we say the answer is 4 Newton, right? Now on the what? Think on the other way around. I will give 4 Newton here, use 6 minus 2. Okay? Use the directions pro your resultant subtract with that. Then
so whichever way is going, the direction is the
yeah, if you make it
stronger one.
because you say it's I'm going to take a positive 1 point. Okay, correct? So that means you take upwards positive. Okay? Otherwise you take downward as positive also can, then everything minus. Okay? So from there, 700 divided by G, you get back the mass. 1.8 is here. The scale reading is it should be on normal reactions. So you plus back your 700 Newton of weight. It should be your answer. Got it?
So MA equals N minus W.
Yep, in this case. Okay, if you got fluid
You
upthrust,
need to define where acceleration is first.
Yeah, they got to tell you, right? And then up to you, you write positive 1.8 as your acceleration. That means you're taking the direction of acceleration as positive. Then you got all the positive vector, the N, minus away the negative vector, the W.
Actually, I still don't get the N minus W thing. I know it's this way, but I don't know the logic, the thinking.
The thinking behind is try not to think in terms of physics. If you're familiar with AMAX, okay. Actually, anyway, it's okay. Okay. Now, just now I mentioned this. You have a N upward, you have R downward, right? You have accelerations, but not R downward. It's a W downward, and you have accelerations upward, right? Okay. So it's up to you, okay? Because this is 1.8. Okay. Now you say, oh, I don't know what to take positive, and I don't know what was the reason. Then don't care. Okay. You take upward. If you take upward as positive, okay, or otherwise you use downward as positive, it's okay. Okay. You take upward as positive. What I'm gonna say, I will say is that resultant force equal to the resultant force. Okay, so resultant force equal to what? Equal to MA. Okay, and I think upward is positive, right? So it's a positive N plus a negative W. Got it? Okay, then I say this is 1.8 and minus W. Okay, or if you take downward as positive, okay, I'll say MA downward as minus N, now just for the sake of my explanation, so I will just put in a corresponding position. Okay? Okay. It is not about which minus which, it's about which direction you should take as positive. Then you substitute the right value inside.
The question, right, is it advisable to always define acceleration in one direction?
Always try to define acceleration as a positive direction. It will be a lot easier. Okay, because acceleration is.
But this one is like up down.
Yeah.
So do we like for all the different parts we take acceleration downward as positive and do, or for each part in the same question then change accordingly?
You change accordingly, yeah.
But it's under one question.
Yeah. Otherwise you do it this way. You set one side is always positive, so when you say downward is downward 0.6 there on things, right? Substitute minus 0.6, substitute minus 0.6 inside here, then you still say upward positive, downward positive. But to me, I would say is that always try to fix direction of acceleration as positive is the best, because acceleration is the overall effect of all the forces. So that means, right, if acceleration tells you is that direction, right, you know that direction's vector sum is certainly bigger than any other direction's vector. Okay? So it's always better to do it that way. But it's okay if you want to do it this way, you will still get the same thing. Okay, just make sure that when you substitute A at the time, substitute the correct direction A. Okay? Okay, all this. Okay, but my advice is different part use different things. Okay, the second thing, still in here, I want to talk about is the slanted, it's some slanted surface. Okay.
This one is it?
Yeah, it's a standard one. It's either horizontal, vertical, or slanted, right? So slanted. Well, when we have slanted, there are a few tricks you need to know. Okay, if an object either going up or going down, I don't care. Okay, a few things. You must be able to consider them as two-axis component, and but do it wisely, because if an object is this way, it's either sliding in this way or sliding in this way. Okay? If it is in static, it is under chapter of forces. If it is constant speed, maybe it should be in the kinematic chapter. Okay? But now if it is have acceleration, so it's in dynamic chapter. Okay? So if it is in this chapter, it is either moving left or right. So there's two conclusions you must say is that first, I will see the overall effect of my object is along this axis. Okay? The overall effects will not have any component other than this axis. Make sense? Okay. Second things, right? It says that up down, right, got to balance. Otherwise, this object should be accelerating up or down. If it's not accelerating up or down, we know the slide along. So the up down got to balance. The forces got to balance. So how to do all these things, right? Is that okay? Is to know about this angle theta. Okay. If you have this theta, and secondly, right, you try to draw a lot of things, okay? Let's say you have a frictional force in this way, okay? You have a weight in this way, and then you have a normal relation R in this way, okay? So if that's this case or some other forces, try to resolve in the along the surface and perpendicular surface axis, okay? Because the idea is that perpendicular axes are equal, and this axis will give you the resultant motion. So in this axis, where we focus on resultant force equal to ma. Okay, but in this axis, right, we say ups equal to downs. Okay, so when they balance in this way, ups equal to downs. When they have not balance, f equal to ma. Okay, when they balance, then left equal to right, the kind of things. Okay, so after that, right, in this case, how do we resolve it, right? Is that when you have this, right, we don't know with this axis and this angle, we got to be theta. And this got to be a 90-degree hypotenuse. We're going to make a hypotenuse, then you make it to two components, okay? You know why is it theta, right? Because the 90-degree minus theta and those things, okay? So this is actually, if this is a W, so this is W cosine theta. This is W sine theta in these directions, okay? This one resolved to along this axis, and in this axis, perpendicular axis, and along surface axis. Okay.
How to find the friction?
Yep. So, what before we say how to find whatever, okay? So what is the possible formula that I can ever form? Okay. The idea is this and this. If you have this idea, up, zero, down, you say that the R and this component is got to be the same. So R equal to W cosine theta. Okay, that's what you know. Okay, but in this axis, we say this is what I'm interested. Okay, that means resultant force equal to ma, right? So I know that if the object is accelerating that way, I will try to take that way positive. Okay, so it says that all this side force minus that side force will give me the resultant force. The side force is long if it's accelerating down. Okay, if it's accelerating upward, I will say that this force is greater than that force. Okay, so what can I say if it's sliding down? I'll say W sine theta minus away my friction will equal to the ma. Okay? Then if they give you acceleration whatsoever, you just go find the value. Okay? The idea is that if they balance, forces equal. They're not balanced, F equal MA.
If it's moving up, then will be
I will use the
tension, is it?
yeah, you may have
Tension
tension or
minus
maybe
W.
some driving force or whatsoever.
So it's driving force minus W sin theta, is it?
If the driving force in this way, then I think your friction will be in this way. Right? If you're accelerating upward.
So it's driving force minus friction minus
Yep.
W sin theta.
Good.
Oh, okay.
Equal MA. Okay? Great. Okay. So tell me, right, something they want, they sometimes they're not interested in so much about calculating and get the answer. Okay, nowadays. They want to ask you a lot of theory things. So tell me, this up 0 down, right? Okay, you say this is the equations, right? But what is your rationale behind?
Newton's third law.
Newton which law?
Third law.
Third law. What do you say?
Huh?
You said this equal that, up equal down. What law is that? Newton which law?
Third.
Your third also.
Yeah.
Wrong. Newton first law.
Huh?
First
That
law.
one is when it remains constant without force. Oh.
Right? That's Newton first law. You realize that my rationale behind actually is not this, you know. My rationale behind is actually resultant force equal to 0. R minus W cosine theta equal to 0. Right? Therefore, you bring over, you have R equal to W sine cosine theta. So if they ask you which law tells you this, Newton first law. Newton first law always tells you when object is not in translation motion. No, sorry. When the object is not in translation accelerations, okay, all the forces got to be balanced along that axis. Okay, so this is actually Newton first law. Okay, so here, this one,
Huh?
in this axis, what law is that?
Newton's second law.
Newton's second law, right? This is tells you the Newton's second law, right? The resultant force will give you a real change in momentum, which is your MA. Okay, so tell the right force, okay? Tell the right thing. So what happens if they ask you for Newton's third law? If you talk about Newton's third law, it's talk about this with this. Two different objects. Okay, force A on B, force B on A. Okay, so what's on B, what's on A? If you just talk about one object right there can't be any Newton third law. Okay, great.
For this W cosine theta thing, right? There's not much use. They can't really ask us, right? Except for theory. For calculations, there's no.
Not really. I think sometimes they may want you to use the. Sometimes depends on how evil they are. If they give you the value of normal reaction, no, don't tell you the
So
rest,
that,
right?
there's,
Then from the normal reactions and the angle, you can deduce the weight, right?
yeah.
From the weight with friction, you deduce the resultant acceleration and such things.
The normal reaction is the R, right? No, right?
Yep. Normal reaction is the R, right? Just now my R. Okay. W and F, right?
Yeah.
What if they ask you for accelerations in this way? If they give you this, but they don't give you this, but they give you this, and the angle. Okay? So from this, right, you need to find this component.
Then
From this
find
component, you find W. Find the W,
then
you
find
have this,
sine.
this minus
Sine.
this, then you, yeah. Yeah, so careful, okay? Okay, for the translation things, okay, then we'll go for the impulse, impact, or something, and the collisions. Linear momentum, on next chapter already. Cool. Okay, now, something about the,
Oh yeah.
right?
Question 11, some theory question.
Okay, question 11. The little sister won on the right her stack on the ground resistance. Okay, yep.
Yeah.
Now, here, right? She's sliding. Okay, so she have her weight.
11.
Yeah, 11. See,
Oh,
下面
okay.
看 the whole question is about the figure A or figure B, if they use the same force and same angle, which is more efficient, or which one have need lesser force, that kind of things. Okay, alright. They just say which one is easier, like lesser force. Okay, so let's think this way.
Technically it's B, right?
Yeah, it's B. Right, it's B.
But how to describe?
First, draw out all the forces first, then come out the resultant force for the same acceleration you need to reach. So same acceleration you need to achieve. Compare the two forces that you apply to in the equation. Then you see that something is plus, something is minus. So the plus one certainly is more than the minus. For example, if you say the force equal to something plus ma, another one the force equal to something minus ma, then you know that this certainly is a greater force than this, right? Okay, kind of thing like that. Okay, so how to do? First, draw all the forces you can have. So the girl is there, have a weight on Earth, right? Okay. Secondly is that it has a normal reference from the ground, right? And then thirdly, you have frictional force. Okay, if you travel in these directions. Okay, frictional force in this way, because this is actually what you can overcome. So now the problem is that you apply this force or apply this force. I call it F1 and F2. Okay, which one is better with the assuming the same angle? Okay. So in case one, right? In case one, we say that when it, sure. Can I continue with you?
Can.
Yeah.
Okay. Now, so if I need to push, right? Firstly, I'm not going to push her into the ground. Okay. So the normal action will keep changing according to how much force I push in to balance it. Okay, so I'm not interested in up-down motion.
So what's the opposing force of this? Friction.
You see any horizontal force, because the overall effect of acceleration is horizontal, right?
Her weight
So
doesn't matter, is it?
her weight is for no component that which is in my interest. Okay, what's my interest? My interest is they will move. Okay, to be more exact, what is the move? Actually, is you can accelerate. What does it mean accelerate? Because you're interested in accelerations. So that means what you're interested in is the direction of acceleration. Direction of acceleration is in this way. So you're only interested along this axis.
But the larger the weight, the more friction, the harder it is to push.
But when the friction is actually, let's say, equal to mu n, right? Yeah. If you assume different frictions, right, that's another different story. The friction will get even higher, but doesn't matter. You just make it, okay, let's call it friction 1, friction 2.
Okay. How will friction change when the weight increases?
Yeah, friction will increase when you
But
have
they
the
are
press.
both
It's even worse.
it's perpendicular. Right?
Sorry?
The forces are perpendicular to each
Yeah.
other.
It's due to the roughness of surface.
Oh.
Yeah, it's not any vector of shadow of the normal directions will be imparted into the friction node. Okay, there's no relationship. But the point is that like this, friction. Like this is more friction. Okay, so there are some relationship, but it's not due to any force in here. But it's due to this one pressed on the surface and the roughness of the surface, right? Got a lot of small gaps. So you press even more, right? The slanted normal directions get greater value.
Oh.
So the components will get greater, kind of things, okay? But don't really care about it. So friction 1, friction 2, you want to do about it, okay? R maybe R1, R2 also. I don't know, okay? Getting more and more variables. Wow, this is complicated. Okay. Unless we assume that F and R is different, but we don't care about vertical components, okay? So my interest is along the accelerations, okay? So just horizontal. So in case one, right, I have an F. What are we solving this way? Okay, this is a theta, F cos theta, the right side, okay, minus friction equal to ma. Okay, makes sense, right? Friction 1, okay. Got it? The second one is F2. Okay, in this case, I will solve in this way. So this is F2 cosine theta. minus F1, F2 equal MA. Interesting. Okay, so they both have F1 cosine theta equal to MA plus F1, F2 cosine theta, MA plus F2. So the idea is that which friction is higher. Okay.
We can't derive.
You can derive friction equal to mu n.
Huh? Like,
Yeah. Friction is proportional to the normal ratio because the normal ratio is R, right? Will be different.
but without that formula.
Without the formula, is there any other way to?
Do you like assume friction is the same?
No need. No need this. No need this. I think too much. Just do the vertical component we do. Yeah. Vertically got a balance in both cases. So the case one, right, F1 sine theta equal to F1 sine theta is downward plus W equal to R. What? F2 sine theta plus R equal to W. Okay? So,
but now you need to show the relation with that to friction really, right?
do I need that?
If not, the vertical components won't actually affect the strength that you need to push.
What is R minus, what's W minus R, what's R minus W?
R will be W.
R will not be W, right?
Huh?
R will be W plus this. R will be W minus this. We'll keep this. R minus W, W minus R. So which one is greater? W got to always greater than R. But there's no way you can relate it. What do you want to do? Is it an example? No, right? It's a question, right? Okay. So make it the mu n. Okay. Make it the mu n. So this n1, this n2. Yeah, make it the mu n, then it will be fine. Okay, so here, give me n1 equal to f1 sine theta plus w. This is n2 is equal to w plus a minus f2 sine theta. Okay. So if you replace this for these things, inside back this one n1 and this one n2. Okay. Now the mass is not, the cosine is the same, theta is the same, mass is the same, acceleration is the same. Let's say achieve the same accelerations. The mu is the same, so roughness of the surface. And then inside the n1 and n2, right, this is a comparison. The w is the same. Okay? But then one is a plus and one is a minus. Okay? So you know, once plus minus in this way, this is always positive, you see? Okay, that's how we define. These are numbers. Okay, because I take out minus because I take out direction. Right? So one is all this thing plus something, one is all these things minus something. Okay, so this is why the F2 is a smaller force than F1. Okay. Okay, right? Is it any easier way to explain this? Take moment cannot. Can't. Yeah, they're all at the same point. More or less the same point. Okay, can I rub?
Yeah.
Sure. Any other questions? Want me to try?
I have assignment 3.
Assignment 3, yeah.
The pendulum one.
The train is moving along a straight horizontal track. A pendulum suspended from the roof carries train is inclined at 4 angle to the right and calculate the acceleration of the train. Okay, so the train like that, pendulum like that. I think
4 degrees of vertical.
it should be this way. Make sense?
We can
Yeah.
be faster.
Sorry? No, the idea is that if the train already reaches steady speed, right, then the pendulum also should reach a steady speed, right? Otherwise, the pendulum will keep moving behind or keep moving behind, right? So if you talk about this, I think it's you have a forward acceleration in time. When your train start to accelerate in front, right, your pendulum is yet to accelerate in front. Then at that instant, you can have a 4 degrees Celsius that the train is going to pull the pendulum move also. Correct? Correct? Okay, so I think it's accelerations 4 degrees.
Vertical.
And they asked me to find acceleration, right?
Find acceleration of train.
For the train, okay. The pendulum, the mass, any mass or
Never give.
never give up.
Never give mass of train.
Wow, cool. Okay, so which is the object that you want to concern?
The train.
The train or the pendulums?
Train.
Okay. Yeah, but train got no money. Now, if you talk about train, right? Train have been pulled by the pendulum. Train have frictions. Train has driving force. Train has train's weight. And got nothing to do with the 4 degree, right? So the object in your mind shouldn't be the train, unless they give you those details. Okay? So what do you think? We left the pendulum. Okay. So let's just talk about pendulum. So assume that the accelerations of your train is the same as the acceleration of the pendulum. You keep accelerating with constant accelerations, right? The pendulum also need to keep accelerating the same accelerations. The acceleration got to be the same. Otherwise, the pendulum will go to front or the train will go to front. Okay. So if it's constant 4 degrees Celsius, when they keep accelerating, so this is the instant. Okay. What do I have? What do I have? Tension, right? What else?
Wait.
Weight downward. Okay. And is it balanced? Of course not balanced, right? How can it be balanced? These two forces, you don't have left hand side force to balance it. If it's balanced, it shouldn't, you know.
This happens only in one instant, right?
Not really.
Because there will be the acceleration this way. Right?
But the idea is that what if you keep accelerating? If the train keep accelerating, the pendulum also going to keep accelerating. And while they both are keep accelerating in the same amount, they will keep the 4 degree and keep going. Okay, so that's the idea. It's not the first jerk, it's not the constant speed also, but it's in the instant you keep accelerating. So like that. Where is the pendulum accelerating? Because it's in dynamic, right? Okay. So answer is this direction is accelerating, or this direction accelerating?
Horizontal.
Horizontal, right? Nothing to do with this, right? The pendulum is not going this way, but it's accelerating in this way, right? It's not going up down also. Okay. So then the acceleration got the same as the train's accelerations. Okay. So this accelerating this way. So accelerations in this way, right? I'm interested in this axis forces.
So it resolve the tension.
Yeah, but we resolve the tensions with MA, right? Okay, so we say MA of the pendulum is equal to T psi 4 degree. Make sense? Because there's only one force,
Oh wait.
the horizontal, right?
But T is this way.
Yeah, you accelerate it that way, right? I don't know whether I can do it for you. Okay. The initial jerk, the time, right, you will have some degree. But once I reach a terminal, I reach a constant velocity after I increase, right? Then this one will go back to like that. Then we to get like that. We will keep accelerating, 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 accelerating. They will going to keep accelerating also. So this is the fixed angle like that. Okay. So the tension is in this way, and the object, the pendulum, is moving to the right. So, got it?
Doesn't it be like negative t or something?
Where is it accelerating? Right or left?
No, but the t has no direction, is it?
T has direction, of course.
Do we need to add the direction in?
Yes, T direction is here, right? Okay? But it's not the whole T is the resultant force because the object don't travel in the object is not accelerating in
so
this way.
t sin theta is which direction?
T sin theta is here.
That way.
Yeah.
So it will be
If this is a theta, the theta is a vertical, not horizontal, yeah? So this one opposite to the theta is always sin theta.
Yeah, I know.
But in this
if
in
it
this
moves
way.
with the same direction as MA, then
Now MA is not a force, right? MA is the resultant force. So the T is the MA. Because if there's only one force, the one force got to become the resultant force. Okay? So this is T sin theta, and this is the resultant force. There's no other force. So we have this. Okay? I need to find accelerations. I need T and M. Okay? So you may need another equation. Okay, so consider up down. Up down is balanced. Right? It's not accelerating. So that's why you have mg equal to T cos theta. Okay, which is the W downward equal to the upward components T cos theta. Okay, I'm interested in A. I don't want M and T dy. Okay, A over G equal to tangent 4. A is equal to G tangent 4. Got it? Okay. So the idea is that in the dynamic chapter, right, most of the time system will be a bit complicated or sometimes too simple. Okay, just cannot visualize. So what can you do? Is always come up with a diagram, draw all the forces, and you're going to ask yourself where is the direction of acceleration you're interested. Resolve along there, and then check the vertical component whether it's theta or not. If you can solve it, straight away solve it. If you need extra component, says that vertically is balanced, so up force equal to down force. Get you another equation, 2 equations, look at it, see what you get, and normally you can solve it. Okay, now solving this kind of dynamic questions, right, have a few tricks. The first trick is like this. Okay, the second trick, right, is that especially when you have a block with a block that kind of thing that you have one force in this way, that kind of things. Okay, there's another one for that. Okay, how to do that? Okay, just to list out all the equations. Okay, for simplicity, we do 2 objects. Okay, let's say A, B. Okay, then we say let's say I have a force F on A. Okay, here, and then let's just have a friction of A and friction of B separately. Okay, if you combine that means that both friction are together also, and then you can let's say R, I don't know, okay, the end of A, okay, the weight of A, okay, then the end of B, and then the weight of B, kind of things. Okay, and let's say you have acceleration this way. Now, how to link all these things up? Okay, the first things, which is the most useless things that you shouldn't consider unless you really need it. Okay, don't consider it. Okay, is to because when you have accelerations, this is always the direction that I'm interested. Okay, so the extra piece of information is right just to see whether it got use or not. Otherwise, got no use. Reason, Newton's first law. It's not accelerating nor upward or downward. Okay. Okay. So second thing, okay, is horizontal. Now horizontal is interesting. We can how many different kind of consideration we have? In this case, 3. What are the 3? Is A, B, and AB. Okay. Sometimes you need to use 2 of them. Sometimes it's faster to use A, B together. Okay. So the case 1 is A. Then you separately draw the object A, right? I'm interested in horizontal, so I'm only interested in FA. Okay, and then this is the force B on A, if I write this way, okay? These are two different forces. And then it says that the friction on A. Okay? Any more? Friction on B, it shouldn't got anything to do with friction on B is the distance between B on the floor. I'm sorry, the floor on the B, okay? So this is the floor on A, this is from B on A, this is the force that apply on A. Okay? So in this case, right, actually you what kind of equation you can have, right, is this. You can have since it's accelerating to the right hand side, the whole system, I can say is that the mass of A times A, the acceleration is equal to FA minus FBA minus, plus FA. FA, sorry, wait, I'm confused. Minus, okay. Okay, this size force minus that size force. Okay, this is right side force, this is left side forces. So the right side force minus away both left side forces. Okay, inside all these are only number. Okay, then this is the first equation you can. Now we have object B, right? Okay. This one is on A. B only experienced force and a contact force from A to B. This force is not on B, right? So you only have one force of B on A, and you have a friction of B. Okay? And then what equation do I have? I only have this. The mass of B times the same acceleration, because they are moving together, so all the acceleration is the same. All the kinematic are both the same. But you got the right side force FBA minus away FB. Okay? Now, careful about this, okay? I have already taken care of the minus sign. That means the direction is already taken care of. So inside, right, is all the numbers. These two numbers may be, did I write something wrongly?
FAB.
This is AB. Yeah. Okay, so this is AB. Okay, the idea is that this number and this number got to be the same. So FBA is equal to FAB. It's not FBA equal to minus FAB because I already taken care of directions. Okay, so put a number there. Okay, be safe. Okay, so this is what I can say. But the third instance is that I can consider AB together. This actually most of the time is quite powerful. Okay, so the idea is that I experience the FA, and I have two frictions, and I can combine the friction as FA plus FB.
But this is only if you know a lot of numbers.
Not really. If they give you not enough number, more time you can count this. Because in here right now, you see so many variables, right? In here, no, all this will not appear. The BA and AB will not appear. You only have mass times accelerations equal to FA minus rate of frictions. Okay? So most of the time, right, these kind of questions, you can list out three equations. But from the third equation, straight away you can actually get the acceleration easily if they give you all these things. Because there's no internal force. But the bad part about considering this is that the internal forces are disappear from your equation. So if they ask for how much force is by B on A, that kind of things, right, this equation cannot tell you the answer. You need these two. But the point is that always good to use this to find acceleration first, put the same acceleration inside here to find whatever it is. Okay, try to take the right hand side one because this is only have two forces. It's a lot easier. Okay, numerically this one is equal to this one. Okay? Careful, okay? So list them out is not normally can help you solve all these kind of questions. Okay? Good. Any more things you want me to try or questions before we come to the impulse and such things? Or you want to try a few questions? Before I proceed to the next one?
Question 2.
Question 2. Okay, this is another kind of things, technical tricks you need to know. Okay, the idea is to use a equivalent concept, equivalent system. If the system can be resimulated as another kind of configuration and it makes sense to say that they're the same, right? You can treat it in an easier model. What talking is this? If you say I have an object in this way, pull in this way, under the pulley and pull in this way, okay? This system is equivalent to having this object on this surface pull the same force. Okay? So consider a horizontal movement with don't know how come you have this kind of force in left, right? It's a lot easier to talk about all the tension here, the tension here, tension on the object at W. Say, because you're treating the T as a separate, the Y as a separate object, right? Then you got all the T. Okay? But you consider them, this one, right, can be put in this way, just pull horizontally with some mysterious force, right? They should be equivalent. And that's a lot easier to calculate this way. Okay? Okay. And one more thing I need to tell you is the idea of a pulley system, okay, and a string. If it is free to roll, right, okay, everywhere of the tension is all the same. Okay, so if you have things like things hanging this way, a free pulley this way, you have two string wire in this way, and stick on the wall in this way. Let's say one up and one down here, okay? Okay? The T here, now you talk about this object, the two T here is the same value. They can be different angle, but the value must be the same. Because if it's not the same, it can slide until it's the same again. Okay? And if you talk about this knot, this is the same T, this is the same T also. So long as free pulley, it will slide until the T of everything is same. Got it? Okay, so this is the system, okay? So angle can be different, but the two T value got to be the same. It's a free pulley. Good, okay, question 2. So a block of mass M over something like that, okay? You have M1 pulley and down with something like that. M2 block of mass M over the frictionless surface, so it's smooth. Connected by a light small frictionless pulley and a second hang block of mass M2. What is the acceleration of the system? And what is the tension in the cord connecting the two blocks? Okay. So, up to you. Also have 3 models. The first model is that you can consider. First model is you can consider M1. If it's M1, right, I have weight, normal reactions, and tension. Okay. If I'm considering M2, right, I have tension and weight. Okay. But when we consider a simulated system, it can be simulated this way. Reason? Sorry? Now, the reason is when I do this, right? Okay, this is similar to 2 blocks in contact, but now these 2 blocks are in one string, and this string is always taut. It's not slack. So how do I have all taut or all slack or touch together? The displacement, velocity, acceleration must always be the same. Okay, so again, this is kind of things like the kinematic variable got to be the same.
If you draw it like that, means the tension is MA.
No, the tension is between M1 and M2, right?
Then where's the tension for that?
Here? No more. Like just now, the 2 blocks. When I consider the 2 blocks together, right, all the force by A to B, B to A will not appear in the equation. Okay. So in this case, right, if I simulate this object, you also cannot find tension anymore. Because tension is the one that this block pull this block pull this. Okay, it's the internal forces by M1 to M2, M2 to M1.
The tension is the tension created by M2, is it? Not by M1.
Yeah, but at the same instant, your M1 is still pulling M2 back to drag its positions, right? M2 without M1 will just fall in the greater acceleration. Okay, but because you have a tension, then it will also pull the same amount. Newton's law. Okay. This is weird if you can think about it, but actually you don't need this, but you have this, is a lot easier. Okay? Because this is the weight of 2. So if you have this concept, right? Okay? But this cannot help because they ask for tensions, right? If the question asks you to find A and such thing, this is a lot easier. Acceleration, straight away you can find it already. Okay, the only force is the way of 2 because the only force here is this externally. Okay, internal force doesn't appear. This is an external force. Pull on this, and this will act as if a simulated model like that. Okay, but the bad point is about this, right? You combine them, you can never find the internal forces. Okay, but you can always find acceleration in a very fast way. You don't have the two simultaneous equations. Okay, understand this? Okay, the force equal to ma. Okay, and it makes sense in this case also. Okay, but you can't help. Don't help me in this question. So anyway, in here, okay, I know that this I don't care equations, right? You have n1 equal to w1, okay, but I don't care, actually not much use. Okay, so I'm interested in this. So T, the tension, is equal to m1a. Okay, I think I'm more interested in these equations. And here is accelerating downward, right? Because when you're accelerating like that, you're accelerating downward. Okay, otherwise it remain unchanged, you've got to remain unchanged. If it move, it start to accelerate, you keep accelerating. Okay, so it's accelerating downward in this direction, so acceleration. Okay, so this is accelerating downward, so I have W2 minus T equal to M2A. Okay, and what they ask? They ask for what is the acceleration of system. Just like that. Acceleration of system like that. Okay, A is equal to W2 over M1 plus M2, so it's equal to M2G over M1 plus M2. Okay.
Yeah.
If you use this method, but in this method you also can find. Okay, because if I take A, this is M2, this is M2G. Okay, the only problem is my T only. So you add it up, right? Add up the left hand side, you have this one plus 0 equal to M1 plus M2 and A. You divide it over, you still get it. Okay. What is the tension in the cord according to the two blocks? So you want to find tension is like this, right? So T is equal to M1 times acceleration, which is W2, sorry, M2G over M1 plus M2. So it's equal to M1 M2G over M1 plus M2. Okay? Any others?
No.
Okay. Proceed to 5 o'clock. Yeah, let's do a bit more. Yeah, drink first. Okay, in-house and momentum. Wait, okay, I can remember. Okay, just now, right, we say the Newton's second law says resultant force is equal to rate of change of mv. Okay, so we treat mv as one variable now. Okay, so if this is the differentiation, right, this will be the integration. Right?
Yeah.
Okay? Or I just say change mv. Oh, yeah, this is better. Okay. So if you want v final minus v initial, okay, so just final minus initial. That means the idea is that if you have a force time graph, okay, if the force is constant, so nice. Okay, let's say this is from 2 seconds to 4 seconds, okay, with 10 Newton, okay, a force applied on an object, okay. The idea is this, okay, this area, which is this, okay, which is equal to 10 times 4 minus 2, right, will contribute to the change in momentum, okay. So what does that mean? That means, right, this amount of things divided by the mass will be the increase in speed. Increase in speed from what? From the instance of what's the speed value at t equal to 2 seconds until t equal 4. Okay, that would be increased amount. So the idea is that, for example, if you have a person having a short put, okay, so most of the time he's having a constant force. Okay, let's say it's a constant force to push from this way until the short put leaves the hand. So this instance, right, there is a force. Of course, not so possible to be a constant force. Maybe force in the beginning is high and then kind of things like lower, the kind of things until you leave the hand. Okay, so if you talk about what is the final speed of this short put, right? Okay, you can, if you have the FT graph, okay, the area in the graph will be the amount of impulse that is added into this object. Okay, and then the impulse equal to change in momentum divided by the mass, right? And initial speed is 0. Okay, of the short put. You know the leaving speed of the short put after its hand. Okay, so what's the interest of impulse? The interest of impulse is that when the force is applied on the object through a period of time, it will either increase the momentum or decrease the momentum of the object, or increase in speed or decrease in speed of the object, depends on how much mass they have. Okay, so that is the momentum. Okay, so impulse have two concerns. First one is that when you start to create motions, you have force time added on this object will keep increasing its momentum. So it depends on how much mass you have increased speed. Well, on the other hand, when this object smashed something, okay, you have a negative force added on this object, which will cause it to change the momentum or retard it down also. But when the mass is great, right, you can't quite stop the speed. Okay, so for example, if something like a lead ball throwing towards you, right, however you want to push, right, you may not be able to stop it easily. Okay. So what to be careful about all these things is it's very confusing. Okay, now pay very just pay attention. Okay, very careful about this. All the students most of the time get wrong because of this. Now when an object is hitting another object, let's say throw in this way, the two things smash in this way. Okay, with the time t, they hit one another, right? So what is the issue here is that you have the force of this object added in here. B on A. This is the force. A on B. Okay? And let's say they say that it hits a 10 Newton, okay, for an object which is, let's say, a 5 kg, okay, for, let's say, 2 seconds. It can touch for 1 to 2 seconds, but in the 2 second of time, right, let's say it's traveling initially at 4 meters per second. This one initially traveling at 2 meters per second before they hit. Okay? So what happened after 2 seconds? Now, this is the careful things, okay? It says that impulse F times T equals delta mv. Okay? That's what you want to say. So, the F is 10 Newton, the T is 2 seconds, delta mv, right, is m, which is 5 kg, okay? V final minus V initial. What is the V initial?
0.
No. Right? This is before it hit, right? It hit for 5 seconds, right? What's the V here? Both of you let oxygen. 4 meters per second here, okay? So what should I put here? Initial. 4, right? Is it 4?
Starting is 4.
4? No, it's minus 4. Now, if it's 4, right? Okay, it's 4. So then you have 10 times 2 divided by 5 and then plus 4, right? Okay? So that means, right, after I get, right, it's kind of things like 20 divided by 5, so it's 4 plus 4 equal to VF. My VF equal to 8. Okay? I'm traveling at 4 meters per second here. After this impact for 2 seconds, will my object travel even faster with 8 meters per second this way? It doesn't make sense, right? Okay, so where's the error?
The direction that we.
Yep, so in here, which number is error?
Are both the same size?
Sorry?
Are both the
Same size, yeah. Yep, same size, same.
one is 2, one is 4.
Yep, different initial speed. This is 2 meters per second, this is 4 meters per second. Okay? Okay? So I'm talking about this object first.
We can just do V1, V2 equals to.
No. That one only it is after collisions finish. Right? But what is I say at the 2-second instance, that means the whole process we hit until it's smashed and then you leave may take 4 seconds. But I just want a 2-second instant, that instant what's the speed? Okay, they haven't really collide finish. Okay, that's how detailed impulse can be. Impulse can be any intermediate moment. Okay, later constant momentum is defined as the impulse afterwards, after they live with one another. Okay, well, anyway, let's focus in here. So if that's the case, when my VF is wrong, so which variable is wrong? Because this is got to be my equation. This is final speed, this is initial speed, this is the T, this is the F. Which variable is wrong? You can say 2 things, okay? 2 answers. Both are correct.
The 4 can be wrong, the 10 can be wrong.
Yep. So 4 should be what? And why?
Why 10?
Why? Sorry? Why 10 is it?
No, why is 10 wrong?
You can say 4 is wrong. You can say 10 is wrong. Cannot say both wrong, okay? Either fix a 10, you put minus 4. Or you put 4, you put minus 10. You will know the reason. The reason is that in the instance, right, I use this formula. When I put it as positive 10, right? Okay? So this is very important, okay? When you put this as positive 10 at the time, you already assume the direction of the force is positive direction. Got it? Okay? So when you put a 10 here, you already say left hand side is positive automatically. Otherwise, you don't put a positive 10 here, put negative 10 here. So you say this is positive 10, right? Your initial speed is minus 4. Now this minus is because it's a change, okay? So it's nothing to do with the directions. But inside when you put a vector 4, you're going to put a minus 4 here. Because the initial velocity, if you take left hand side is positive, in this case, it's minus 4. Okay? Okay? So it's different. Okay? You take positive 10 means left hand side is positive, so therefore the initial speed got to put minus 4 because initial speed is in this direction. Okay? Careful? Okay? Now, so what is the okay, so do something. Okay, can you calculate the final speed or the speed of 2 seconds of this object B? Okay, 5 kg, 2 meters per second initially. It's experienced this impact, right? 10 Newton and 2 seconds in this manner. What's the instant of this speed when it's at 2 seconds? 来试试看 try okay. You have paper? Give some paper.
Huh?
I sleep less, so I woke up at like 7.
When is it later?
I slept 2.
For what? Chatting.
No, morning I went to run.
Too tired you guys.
Yeah.
Yeah, just try to verify that impulses.
Did it use the formula F equals mv minus u over delta t?
Yeah, but this is the more friendly one because there's an
ft.
FT. Yeah. The force.
T is delta T, is it?
Yeah, delta T. Change in time. The time. The time is the change in time, right? So equal to delta mv. So take out the m, reset to m times delta v. M is constant. Okay, the mass is constant. Take it out. Okay, so v is equal to v final minus v initial. Okay, so better remember it this way.
So is ball A traveling to the right at 4 meters per second. They hit for 2 seconds.
Yep.
And they move overall into the right at 10 newtons.
Not really.
Then where does the F net come from?
It's not F net. It's the F from A to B.
Oh, so it's B moving.
B moving from the right, A moving from the left, and it hit.
Do we even need to consider B?
Yep, you need, because I'm asking what's the velocity of B.
Oh.
At the instant, now remember, now when we have two objects, they have 4 meters per second, they have 2 meters per second at a time. When they hit, right, you can imagine that finally, okay, let's say finally they go out with 2 and 4. Okay, but that is intermediate. The positive 4 in this way got to somehow become the negative 2 later, right? So that may be in between. So if these transitions, right, takes 4 seconds, right? Okay, the 2 second instance when they're impacting, there can be some value of a velocity.
So they're still moving when they are.
Yes, and you may keep actually smashing with one another at the instant, because you take time to change all the acceleration to another way around. Okay. So we are
ball A and ball B same size.
Yeah, same size. Okay. So cannot use the. So in this intermediate process, right, you can never use the conservation momentum, because conservation momentum is certainly before and after, but impulse can use it at any instant. Don't know, right?
No.
Okay, go again. Let's try. Okay, force, right? What's the value?
Can we use the relative speed relation?
What is the formula? Is it?
Yeah, how are you going to do it?
The force.
Is it on the top one, the circle?
Say again.
Is it the Ft equals to delta mv?
Yeah, yeah,
There's a formula.
yeah.
Very good, right?
You have this,
F
right?
equals delta mv over t.
No, you have this. You have this. Wait, okay.
No, it's from t. Yeah.
No, it's from here. It's from the F graph, Ft graph. Okay, this is the force of during the impact, and during the impact may not be, it may be a variable. Okay, so it's talk about the area under graph is equal to the change in mv. Okay, which is the final momentum minus initial momentum. The reason for this is because your F is equal to ddt of mv. This is Newton's second law. Okay, so if this is the differentiation form, this is the integration form, which is area in the graph. Okay, but the point is that in this case, right, you cannot integrate area unless you take it as an average force. Okay, you take it at this instant is like that, so you take the average value counting like that, right? And this area is equivalent to this integrated area. Okay, so we take the average value among these regions that I'm interested in, if they are not constant. But this is why when you put this cap here, means the average. Okay, the area in the graph, you can say it is integration, okay, of f dt. Okay, but you can also take it as an average force times the time taken, this rectangle. Okay, which is equal to the delta mv there.
How I know the average force?
You don't know average force. So this is why if they give you a constant force, this constant force will be the average force. So if they got to give you questions, right, they got to give you one fixed force, at least average force or a constant force. Okay?
What's the question?
The question is that if they hit, okay, under a constant force of 10 Newton.
When they hit, then
when they hit, right? When they hit, you have contact, right?
Yeah.
You have a normal reaction force, right?
Uh-huh.
And let's say this normal reaction force that will pushing one another, okay, with 2 seconds. Like, let's say the 2 hours 4 seconds, but at the 2 second instance, what is the speed at 2 second instant? Okay, that's the question.
So yeah, 10.
Yep. So let's say in this 2 seconds, always 10 Newton. Okay, so what is the final speed at this 2 seconds?
You want to find the mass of the AO, the velocity, the speed of AOT.
Yeah, the speed of B. Initially is 2 meters per second. So under 10 Newton of force of impact for 2 seconds, what's the final speed of B? Okay, the speed of B is the B is 5 kg.
We only can find A, what?
Okay, let's try to do together. Okay, now this is the equation, or this is the equation. Okay, so remember I say this is if this is constant force or average force, just put it. Got it? Okay. So what's this value here? In this case, 10, right? Good. So what's the time here?
2.
2. Good. This is the mass, right? 5. Final speed is what I want to find. Initial speed?
4.
Initial velocity 4. So I put 4.
2.
It's 2, right? 2. Okay, is a B. Okay. So it's 2, right? Okay. So it's 2 or negative 2?
I don't even know which direction is positive yet.
Yep. But what do you put here? Do you put positive 10?
But 10 is, according to Newton's third law, have both direction or 10.
Yeah, Newton's third law tells you object A, error object B, error object A, right? Okay,
Yeah.
good. Okay. But we're talking about Newton's second law here.
Minus
Is the Newton's second law give you this, right? Okay.
What?
Is the Newton's second law give you all this? It's not Newton's third law.
Is
Newton's third law says this force equal to this force only. Is Newton's second law tells you this one will give you the acceleration and change the speed and such. Got it?
So it's minus negative 2.
Yeah, you're right. Okay. Is Newton's second law tells you that how a force is affecting a momentum, affecting a speed. Second law, okay? So second law says this is the resultant force. That is the force that this object is experiencing. When A and B are hit one another in this way, what is the force added on B? 10 Newton, but which direction?
B is
On B.
on
By A, of course, okay? Right?
on B by A.
Yeah, who yeah, these directions, right?
No, it's the on B.
On B, right?
Oh yeah, sorry.
This direction, right? Okay. So if you say this is the direction and I put positive 10, right?
Oh, okay.
So that means at the instant you're assuming right hand side is positive. Automatically. Otherwise you put negative 10. Okay? So you see one side is positive, right? Then final minus initial velocity got to be. Initial velocity is 2 meters per second in this way, right? Which is against this direction. So you've got to put minus 2. So it's a minus and minus 2. This minus is because it's a change. This minus because of the direction. Okay? So do accordingly, you get it correct. Okay? Can I? Sure? Okay, try one more. Okay?
No, but cannot use this.
Yeah. You can't, okay? Because now, the idea is this. It is from the Newton's second law of this differentiation set, right? They derive the concept of impulse, which is the integration set, okay? In the impulse, right, as what I say just now, the two things that is smash, for this, let's say 4 meters per second, 2 meters per second, this way they hit, right? Until let's say, what if after they hit is 2 meters per second, 4 meters per second, this way they leave, right? There is a time. Okay, there is a time. And from 4 to 2, right, you need to drop to 0 and you drop to -2, right? Okay, so you can see that the speed actually keep changing until positive 4 to -2 in these transitions. And take a time. So let's say the time is typically take 4 seconds. Okay, so what is the speed at 1 second, let's say? That's
So
some intermediate process.
So the equation at the back is only used when
Yes.
they just hit and go.
You're right. This is the first moment and the last moment, because the conservation of momentum, yeah, conservation of momentum, right, is derived from impulse. Okay, it's further derived. Okay, so impulse is very important because people don't know the positive and negative. And remember, right? Okay, just now we did two things. Okay, look here. Now just now we did two things, right? One of the forces in this way, one of the forces this way. So this part, right, the positive negative, right, is interpreted along this positive directions. So you find your answer is -2 sec per second, means that it's to the right side. Okay? And this one, if you say a positive 2 meters per second, is also talk about the right side. Because different part, you use the different positive direction. Okay? So interpret your answer according to what you're doing at the instant. Okay? You automate, because we always very tempted to just put in the positive force, so we will just assign that to be the direction of the positive things. Okay? So test yourself with this. Okay, a lorry is moving to the right with 2 meters per second, very slow, and then a car, right, hits him. Okay, 4 meters per second initially, and this is, let's say 5 kg, and this is, let's say 10 kg. Okay, let's say the force that this one's going to hit here, right, the force is equal to 20 Newton. Okay.
Force of the car hitting the.
Yeah, because the car is faster than the lorry, but they all travel in these directions. Okay. Can? It hit him, but it smashed until it leave, right? It takes some time. But I'm asking for the intermediate moment. So what happened when it is at the impact of 2 seconds? What is this two's velocity? Can you find this and find that? Try 5 kg, 10 kg, this and that.
The car will move at 8, is it?
The car will move at 8, is it?
Oh.
Not logical. I got A also, but I think it's not logical.
Yeah, it will go faster.
That's how it goes, yeah. It should be slower.
Then I put a minus sign, yeah, I got 0.
0.
No, if
It can be 0, why not? That may be the instantaneous
It means instantaneous.
at rest, the instant. But the car at rest need not to be the lorry at rest, right? Makes sense, right? So you don't know, okay? So what do you put?
But your initial has to be positive.
Okay, one by one, what do you put? Tell me your variables. Okay.
20,
20 is it?
2,
2,
Find the car.
10,
10. Good.
VF.
VF. 4. Now, where is the force at on this? When you hit the truck?
This way,
Left, right?
to the right.
Is the lorry pulling you or pushing you?
Pushing.
Lorry to the car is this way force or this way force? Is the lorry pulling the car into me, or the lorry when you hit me actually I'm bouncing you back? How? Is it okay? The force on car is here. By lorry to car. Okay? Because
What this 4 is what for us?
this force is normal reaction force because they touch contact.
This 4 we are putting is the what force on what?
This 4 meters per second
Yeah.
is the initial speed of
Yeah,
the car.
then when we put inside, we take it as the what?
The initial speed.
But the sign,
Sign got to be, say, what do you put here?
Negative 20.
this
Yeah, you can either
20
put negative 20 and this will be positive 4. Because if that's the case, you take our right hand side is positive, right? Then your force is negative. Okay? But if you,
But the force is exerted from your car,
sorry? From the lorry to the car, right?
not from the car out.
Sorry? From the car to the lorry, is it?
This 20 is car to lorry, right?
This 20, no, this 20 is car to lorry 20, lorry to car 20, Newton to law, right?
This 20 is car to lorry to right hand side.
Yeah, can. But you talk about the force on this. Then you don't talk about the force by this, right?
Oh,
But because
okay.
the force by this is on the truck, not on the car.
Okay.
Okay, so this is why this is the force on this object. So if you take this as positive, this got to be minus 4. Okay. Then you have 40 divided by 10 minus 4 equal to Vf. Yep, momentary at rest. Okay. Now try one more. Okay, this one is a bit different because the lorry actually is moving to the front, different from the car issue.
Answer to be
10 is it? Okay, good. So the same things. Okay.
Just 22, 5. VF 2.
And 2. Okay. So 40 divided by 5 plus 2 equal to Vf. So it is 10. Yeah, good. Okay. So it's faster than 2 meters per second push to the front. Okay. Now the effect of putting a minus things, right, you really make something that which is totally out of sense. So every time you do an impulse question, do finish, you ask yourself, does it make sense or not? If not, normally it's due to one flip of the sign. Okay? Careful about this. Okay, so we know how to interpret the positive 10, right? The positive 10, because I take the force direction as positive 20. So and the force is this way, so that means it's the right hand side 20. Okay, if this instance, right, can be that you can see that initial is 2. Okay, initial is 4 in this way, right? At this instant is 0, right? Okay, think about the time longer. What do you think we will get here?
negative.
We get negative. Okay, so when you say negative, it's negative to the direction of the force. Actually, it's to the right. Okay, actually the truck will. So after smash, right, the truck will go fast, but B, right, the car actually will still go to front. Okay, so you can see this kind of impulse.
Maybe this one can also be a conservation question.
Conservation
Because
of.
you see the momentum, the car lost 4 meter per second speed, and then the momentum is 10 times 4, which is 40, and then when
Yep.
you divide.
You're right. Actually, that one you can also treat it as a final moment of momentum conserve. Does it
But
conserve?
they are stuck there for 2 seconds.
Yeah.
How do you smash something when it gets stuck? nothing to yeah.
If you immediately release, then you can use PCLM, is it?
PCLM, yeah. Actually, this instant, if I don't give you how many Newton, how many second, right, you can still use a PCLM. Okay, but you need to know some other variables like the final speed of one guy, you know, to know the final speed. Okay, so it depends on what variables they want to give to you. Remember, impulse is a more detailed version, but principle of constant momentum is just initial final of impact. Okay. Not really. You can't use constant momentum in the in between of the collisions. When you have,
But
no,
for
sorry,
every
you can.
second,
You can. You're right. Okay. Sorry. Good. So principle of constant momentum. You got any issue? Okay. Let's just go through it. Okay. The first thing is that you have collisions. Okay. Collision have how many types?
elastic.
Oh, okay. That's 3 types. Okay. But the models wise, right? You have 2. Okay. You have 3 in your theory. You have 2 in your questions. The first type of collisions you can have is heat. Okay.
Yeah.
Heat or heat. Make sense? Okay. This is one type. Okay. I'm not saying 3 types. Another type, right, is that we have a string. Slack until it jerk. This is a collisions. Okay. Yep. Surprise. Okay. When 2 objects connected by a string, not elastic string, but initially it's slack, right? When one guy move, one guy just move. But when a guy moves certain distance at time, the length is maximum already. Right? You jerk another one, move together. Okay. So this is called you can use the constant momentum in this case also. Okay, I know you know all these 3, I know you know all this, but I want to allow you this. Okay, MCQ and Shopper have this. This
If
is,
they are the same size, then they'll move
Now, it
the
depends.
string taut, is it?
You're right. If it will not be, not same size, right? Same size is about exchange. Same size and elastic, it will be exchange in velocity. So one guy move, one guy stop. Like after you jerk, right, the guy will stop, and another guy will keep moving until you hit again. Then this guy will move, this guy will stop again, and then keep jerk with that.
Why do you keep pulling?
Keep pulling, then you're not having a momentum, right? The momentum is before you jerk and after you jerk. Okay, you keep moving, then you talk about this guy. You mean keep accelerating, is it?
You just like keep moving 5 meters per second with the string.
Oh, together is it?
You
Yeah.
just hold the first
You can do
one.
that, but normally this will not be a elastic collision. This is actually in the third case. Okay, the third, now if the things